Involved with SEDS in his college career, serving as US SEDS president and chairman of the SEDS-USA National Board. He's gone on to become the flight director of the Spirit and Opportunity rovers on Mars, and he was also the surface mission manager for the Phoenix Mars mission. He's going to be discussing his story from freshman year to outer space. So, thank you, Chris Lewicki.
All right. Ben brought himself in the room. I wore this shirt today just because Ben was commenting on Facebook last night how it was disastrously underdressed. So I dressed down a little bit today in honor of Ben. So in the beginning, for those of you who have seen me tell this story before, I've added some new bits throughout. For the rest of you, hopefully it'll be new to you. What got me inspired in space, I'm really not quite sure. It was probably Cosmos and Carl Sagan and those types of things. And I think the first profession I wanted to be was a fourth grade teacher, and that was in fourth grade because I'm a fourth grade teacher. And then I wanted to be an astronomer. And then in 1989, during the Voyager 2 encounter of Neptune, that's kind of when I figured out I wanted to build robotic spacecraft that went to the planets. And there was a brief period before that when I thought about becoming a shuttle astronaut, but then I looked at all the degrees that you had to have and how many years it took, and then how little time that you actually spent in space. I thought it would be much better being a support function. So after that, I went a little bit, thinking about being in a rock band and doing all that type of stuff. But then I came to my senses and said, no, I'll train to be an engineer, and the music stuff I can do as a hobby. So here's my proof. Cat card. Actually, this was probably like, senior year or so. I have to scan in my even older one, where, I'm like 40 pounds less than that picture. So you all saw this picture last night. To embarrass my wife, Andrea's in the picture. I think I pointed her out last night, too. Up above. I can't really point that way because it's projecting in the back. There she is. And Tim's still here. And I just talked to John this afternoon. He's getting his PhD from optical science before too long. So in SEDS, I told you a little bit of all of that stuff I did last night. What kind of set me down the path of my space career was the Mars Observer. I went, before this building was built, I went over to Professor Boynton's office and very sheepishly knocked on the door to try to come and get him to speak for a SEDS meeting. And my duties as vice president was to gather speaker and organize chapter activities. And, Dr. Boynton was, working on a NASA mission, and, he was a principal investigator of the gamma ray spectrometer, and as far as I was concerned, he was God, because he was involved with NASA stuff. And I very sheepishly asked him if he would speak, and he said he would. And we got talking for a while about his work on Mars Observer and what he's doing, and towards the end of the conversation, he's like, well, I'm looking for someone to, help me reduce gamma ray data and stuff like that. Do you know anyone who would be interested in doing that? And being as naive as I was at the time, I was like, I sat there and thought for a bit. And all people I know, it's like, well, I don't really know anyone who's doing it, but I would be interested in doing that. So he gave me a little application, I filled it out, and I was hired the next day. And my office was adjacent to his desk. So I would come in and I would work 2 feet away from him, and for about a year, that's where I worked. Got involved with Susan Brew and Arizona Space Grant Consortium. I applied to the Space Grant Program my freshman year and was rejected. I just found my rejection letter this year. I have to scan that and put that in this presentation. But the following year I was accepted, and I ended up actually doing some stuff on Mars Observer. Even after it crashed, there was stuff we did in cruise for that. So Space Grant certainly shaped me a lot, gave me a lot of opportunity to interact with other people doing research on NASA missions. I told you the SED story. I'll skip right through that. I was talking with Andrea about the conference room that you all just had the Council of Chapters meeting in. That was the room that we had the Arizona Roundtable in. And the other thing that I remember in that room was I was sitting with Dr. Boynton. I worked with him on the first round discovery proposal for the Lunar Discovery Orbiter. And that ultimately lost to the first discovery mission, the, what was it? Not Clementine. Totally escapes me. But anyway, we lost, and it was in that room that we got the bad news. So I remember that well. Worked on other stuff. We'd won a multi-$100,000 proposal to do comet and asteroid penetrators and spent a lot of time with Mike Williams down in the basement of this building with that gas machine firing that test penetrator into 5-gallon buckets of cryogenically cooled sand and mixing up different mixtures and things like that. And this penetrator had a wonderful contraption on it that all worked by fluidics and hydraulics, that once its impact, a little chamber was burst and the pressure fed through and did all these little clockwork mechanisms, and like 10 seconds later it would pop out with the sample in its snout, and then with the big tether that was reeled in the back, you would reel it back up into the spacecraft. So that was a lot of fun to work on for a summer, and doing lots of high velocity braking things. Told you about this already, told you about SL9 already. The next thing that, from a NASA standpoint, that I worked on with Bill after he was doing common nuclear penetrator stuff, we got a winning proposal on the thermal and evolved gas analyzer on the Marsh Polar Lander. And this was probably into my junior year or so. And I got to do a lot of work on that project in terms of, they had these little ovens with a male half and a female half, and they just kind of pressure sealed. And you'd worry about if there was any dirt on there that it would affect the seal. So I did a lot of work trying to figure out how good that seal was and if anything would creep in and measure up the measurement. Also did work on the little LED system that would detect when the oven was full. So we flew that mission, and it ultimately crashed. I didn't actually end up working a lot on TIGA, but it was kind of interesting how it ties in with my Phoenix history. Another thing that we won with Dr. Boynton kind of completely unexpectedly was the contract to do the science database for the near X-ray and gamma ray spectrometer. And this was something that was built by Johns Hopkins University and had a lot of other prominent professors and things on it. And the person who was doing all our database stuff for Mars Observer was the guy who had wrote the proposal. But he left the university and went to Colorado, and Bill didn't have anyone to do that, and I was the second most knowledgeable person on all the Mars Observer stuff, so he asked me if I would want to do it. And my demand was that I had to have a staff job. It couldn't be a student job, so I had to become full university staff when I was a senior, which did wonders for my student financial aid debt. But still, he was paying me, I think I made, as a full staff employee, I was like the lowest possible tier that you could get paid, and it was $15,000 a year, which is pretty good. But the free tuition was really what I was in for, because I think my tuition and fees then per semester ended up being like $350, and that was very nice. Other fun stuff I went off and did with Bill was we had an opportunity. He was president of the, I should look this up because every time I give the presentation I can't remember it. I think it's the University Space Research Association, which is a bunch of academic organizations who all kind of band together and lobby Congress for various things. And Bill had 10 minutes or so to speak before the Congressional Subcommittee on Science at the House in Congress, and he gave me 3 or 4 of his 10 minutes to testify on why space exploration and NASA funding is good for students, and these are my notes from that day. And this was kind of a fun thing. I'd been doing lots of different NASA things and all kinds of leadership stuff with SEDS, and I think I had become chair by that time. But the real interesting part of it was now, it was something where Dr. Boynton, who was formerly of godlike status for me, we had this day, the day that we testified, we were both in the hotel room, practicing our lines essentially. And Dr. Boynton was just as nervous as I was. And it was just a very strange experience to, kind of come to see, this mentoring person that you looked up to all the time. And then that was the point when I found out that he was human. So that was it was a growth experience. It's also very strange to be able to pick up the congressional record and see your words transcribed word for word. But it was certainly fun. This is something that March Storm every year. And, I encourage people to do that at least once when you're a student. It's very fun to kind of go through and tromp through the halls of Congress and try to speak to the different legislators directly. Told you about the X Prize website already. We'll skip right past that. The first year I applied to be in NASA Academy, I was rejected. I have that rejection letter too. Like 2 years later, I applied again, and I had to have Mike Drake and a professor from the aerospace department, is no longer here, K.R. Sridhar. I both had to give them emphatic recommendation letters on why I should be accepted, because my GPA was like a 3.05. And this was a very highly academic thing, but they thought very much that I should be able to go. And they ended up accepting me, except what they also did that year is, this was the year that we set 2, and Daniel Manuzak was another student here. So University of Arizona had 2 students in the NASA Academy that summer. And I'd like to close this particular story off that I showed everyone up, and I won the Goddard Award that year for having the best research project and doing all that stuff. But for those of you who are space grant students, the only way you can get into the NASA Academy is, at least in most places, is by being a space grant student. And NASA Academy just kind of takes it up to the next level. It's kind of ISU while you're already in school. So the network of people that I met there and the other people who have been through the other programs, it's just like SEDS. It's a little bit more intimate because you get to live for 10 weeks with these people and go through a pretty intensive experience, but certainly recommend that. Told you about the ground station, move right on. One of the things that kept me at the University of Arizona, in addition to my wife not yet having graduated, was a couple of professors were starting a satellite project, and they were doing some research on how they might launch this satellite, and Susan Brewer was asking me questions about it. She kept asking me these questions, how we do this research, and then by that point, like the SEDS networks of folk that I knew, and the SEDSAT folks, and the people at Caltech had already done this stuff several times, and I'd interacted with them a lot doing that. So I had, at that point, felt like I knew a lot better than they did how to actually get this stuff started. So I convinced them to let me be the project manager of the UASat, and that ended up getting me a Space Grant Graduate Fellowship, which paid for grad school, so that kept me here. And that was certainly a fun thing to be involved with. I used all the things that we had learned on SEDS in terms of making do with absolutely nothing, and getting free labor, and filling things with pizza and other bribes, and stealing things from department closets, and talking professors into doing stuff that they would really rather not do. But we never actually end up building that satellite, but it went on to become a CubeSat program, and it's had a lot of other legacies. One thing that did not exist when we started that program was much interdisciplinary coursework. If you were an aerospace engineering student, you spent your whole career with other engineering students, and your capstone projects in your senior classes were all with your other aerospace colleagues, and that was it. And what we had started with the UASat was we would try to get independent study programs, so we'd get an electrical engineer, and an atmospheric scientist, and a physicist, and an aerospace engineer, and a mechanical engineer, and an art major, or something. And they would all take this 200, 300, 400 level, depending on what level they were in school, independent study class, and we had convinced the various department heads in all the colleges that they should allow up to 6 credits or something like this to count towards their degree. So we did that. We like this logo we got designed by a competition in the art college here at the University of Arizona, and we got a lot of internships out of it. But I came back a few years ago to give a talk to the engineers breakfast after commencement, and all of the design teams that stood up to make the presentations that morning, every one of them was all interdisciplinary, so it was cool to see that had grown into something else. Another thing, this was kind of my first taste of working directly at JPL. I got to go with a bunch of planetary science grad students here. See if there's anyone particularly of note. No one worth mentioning, I guess, but we're there in 230, Building 230, the Space Flight Operations Center at JPL, and this is the Marie Curie rover, which is the flight spare to Pathfinder. This was just after that had landed, and we were working on Ambassador, which I can't remember what the acronyms expanded out to, something like a mission, I can't remember. It was a rendezvous with an asteroid, land on it, fire these anchors into it take a sample and then launch off. And we got to work with Team-X on that. That was kind of my first JPL experience. I had arguments back and forth with my thesis advisor, Dr. Sridhar, on why I couldn't use the satellite project as my master's thesis topic. And he just thought it was too cliche and it had been done too many times before and there was nothing unique about it. So ended up going through a variety of topics, and I ended up working on, the title was Acquisition and Storage Technologies for Sample Return Missions. And it was about a half research thesis looking into everything that had been done for sample return all the way back to Apollo and the different technologies. And then half of it was kind of a design experiment, and I designed this little kind of, I don't know, it was about the size of an iPhone. And it had ultrasonic motors to drive these wheels and shape memory alloys to push this little plunger down, and then Kapton tape as a sampling mechanism. And the idea was that you could touch down on a surface, the moon, a comet, an asteroid, and just kind of bit by bit take a grain level stratigraphy of the surface, so you could get the entire space weathering history of that thing, and it would spool it all up on the one roll, and then you would return that roll to Earth. So I built that and demoed that for my master's thesis. So that was kind of the end of school. After college, for some reason, I didn't feel that I was quite ready to venture off into JPL. I had actually gotten the job about 6 months before I graduated. I got an interview with them as a result of talking to someone at the Small Satellites Conference when I was presenting the student satellite work. And I ran into the section manager of the system engineering section, and he asked me if I would be interested in coming out for JPL to interview, and I told him, well, I haven't graduated yet, and I don't plan on graduating for another year. He's like, well, come out anyway. And about a half a year later, he wrote me back and said, we're hiring, come out and interview next week. So I went out, and it was the strangest interview I've ever had, because at no part of it did I get the sense that it was an interview. It was more like people petitioning me to please come work on this part of our project at JPL. And it was about 15 different of those things. So it was kind of as a result of all my experience with SEDS and the things that I had done with Boynton. I made this little book of all the projects that I had done that I could show to people. And it was never really an interview. It was just, please come work for us. So even though I had that kind of sitting on the table, I went off and worked on this project with Peter Diamandis and Eric Anderson of Space Adventure fame. He was actually the chapter president and founder of the University of Virginia SEDS. So I met him through SEDS. He was also a NASA Academy alum the year before I was at Goddard, and he had just kind of taken over the reins at Space Adventures, and this was in the middle of the .com craze when everyone was getting an internet site and making millions and buying Maseratis and Ferraris. And so we thought, well, that would be a good idea. We can make a bunch of money making a space website. So we had hired an artist, and we made all these screensavers. We had Ask an Astronaut stuff. We did all these different things, and I kind of went out on the East Coast and lived in Peter and Eric's houses for a few months, and we eventually ended up selling the website to space.com, and we all got stock, which still is worth absolutely nothing to this day. So the first thing I did when I hired out to JPL, and this is kind of the warning that I give to anyone going into big aerospace and big business, is that they give you something completely uninteresting to do and is absolutely not related to anything that you thought you wanted to do when you went to school. I spent 4 months working on a thing called Develop New Products, which sounds cool because, well, you're developing new products, but what it consisted of was going around and trying to write manuals on how you're supposed to do a system engineering job. And of course, being a fresh college graduate, I had no idea how to do that. But the idea was that I could interview people and I could write it down, and then that would become the official JPL procedure, which I thought was rather odd. So I spent the whole time trying to find desperately a flight project to work on. So the first one that I found was the Comet Nucleus Sample Return Mission. Also did a little bit of work on a micro-rover that was supposed to go with the Hayabusa mission to the Itokawa asteroid, but that ended up getting canceled. And actually this one, it was a pre-phase A, as they call it, where they're just kind of studying it. But this ended up getting canceled too. And I was headed up to China Lake Air Force Base in Central California, kind of at the close of this project, to make a bunch of comet corollary things that we could fire a big penetrator in to test our anchoring mechanism. This was kind of the last thing that we were doing on the project. And I had been approached by Peter again and other folks to go work at this other company. And I was kind of dreading having the conversation because I would be locked in a van with my boss for 3 hours driving, and I knew what the topic was going to come up. What are you planning on doing after CNSR? So I had this conversation with her, and it's like, well, there's this thing called blast off, and he was like, oh, you should go do that. And it was like, that's all I got out of my mouth, and she had already known about it. It was supposed to be all super secret. But one of the other people that worked with her also knew about it, and after the discussion with her and a short discussion with Andrea, we decided, well, I'm young. I've only been at JPL 8 months. I have nothing to use. Why not? So after getting my dream job at JPL after 8 months, I quit. And it was a quite shocking thing to do. But I spent the next year working on this very loony commercial lunar exploration thing where we were all going to go and take rovers and land them on the moon and take high-definition video and beam it back to Earth and rove 500 meters. Is any of this sounding familiar? So this, of course, is what has ended up becoming the Google Lunar X Prize, except that we all tried to do it back in the year 2000. And if we all joke as if we had started 8 to 10 months earlier, before March of 2000, when the whole internet imploded and all the stocks became worth nothing, that we probably wouldn't be able to do it, because the guy that was writing checks for it really didn't want to write the next check after his stock was all of a sudden worth much less money. But I got to meet lots of astronauts. One of the most fond memories I have working on Blastoff, other than being able to do things like modify video games so that we could simulate driving in lunar gravity and driving a remote control office or remote control car around the office with a 6-second delay to simulate lunar driving. We got to spend 2 days talking with Harrison Schmitt from Apollo 17 on what it was like to drive on the moon. And I hope everyone in the room has had the opportunity to at least walk up and talk to an astronaut for a few minutes. And if you have an Apollo astronaut, you know that they're even cooler than the shuttle astronauts. But to be able to have 2 full days of business activity, of having a frank conversation, I was like, well, so Dr. Schmitt, really, when you were looking into the sun, what was this, and just to actually figure out how to drive on the moon, talking from someone who had done it, was just a wonderful experience. So after Blastoff imploded, we all got laid off, and for most people, they just kind of went back to their old jobs. JPL told me that they would hire me back, and I would probably work on this rover thing that was getting going at the time. But they were taking like 3-4 months to do that. So in the meantime, I went back to work for Eric Anderson at Space Adventures and did fun things like help them move office and set up phone systems and do their customer relations database and figure out how to optimize their zero-G flights that they had just fought. And that was another fun couple of months. But ended up back at JPL working on the Mars exploration rovers. And I just took this picture off my Facebook page. I liked this picture for a long time. It's taken by a photographer by the name of Norman Sieve, and he is a famed rock and roll photographer who's taking all this famous portraits of bands throughout all time. And they had somehow gotten him in to interview all the big level managers at MER, and at that time I wasn't a big level manager, but I was the guy who ran everything in the test bed, and I was the guy who could set up the airbags, who could bring over the rover, and could get them a pretty backdrop. So I said, well, I would do that for you, but you have to take my picture. So I ended up getting a big interview, and I ended up in his movie, but that's the story behind that picture. So because I've been involved in Phoenix, I decided to put a little bit of back history before I started with MER. MER came out of the ashes of the Mars Polar Lander crashing and the Mars Climate Orbiter not inserting into orbit, and this thing called the Mars Surveyor 2001 lander. They decided to cancel it. One kind of interesting thing, this instrument, the Mars In Situ Propellant Production Instrument, on it had an experiment that was designed and built by the lab that I worked over in aerospace engineering with Sridhar, and I did a minor amount of work on it. But that was on the 2001 lander. But that was canceled, and some of the stuff that they were doing with it, they kind of transplanted over on MER. So they both had the same kind of processor. They were both solar powered. Lithium-ion batteries were a very new thing at that time, and the 01 lander was going to have that, so they put them in the rover. They both had the same kind of communications architecture, which was kind of becoming more mainstream. They both used flash memory for non-volatile memory, which was kind of a new thing. Both launched on a Delta II and both did Mars time operations. And MER, even though the O1 lander had actually never flown, inherited a bunch of things from the design. That Odyssey was going to be a UHF relay for the O1 lander. They were both built at the same time, but they sent the orbiter, not the lander. So MER was just going to use that. They both used a UHF transceiver. I told you about the batteries. The aeroshell and the entry, descent, and landing was similar, except for the airbag part. And then several of the instruments, they actually just grabbed from the O1 payload and crammed them onto the rover. And of course, the O1, or it's not in this picture. Now, one incarnation of the O1 lander was that they would put the Marie Curie rover, the one that was in that sandbox, the Spirit that they built, they would put it on top of the O1 lander and they would like crane it down onto the surface. So MER wanted to do the same thing, but they would just make it a little bit bigger. So this is a fun chart to show. This actually came out May 26, 2003, which happened to be about a week and a half before we launched Spirit. And we were, feeling that we had built something pretty nice and that we knew it was difficult and, it had a chance of failing and whatnot. But the Aerospace Corporation did this study and they said, all right, well, as things get more complex, they take longer to build in order for them to work. And if you're, above this curve, chances are pretty good they'll work. If you're below this curve, chances are pretty good they'll fail. And they estimated that MER was right there, the farthest lower right-hand corner, and they thought this thing is just destined to fail because it was too complex and you built it in too little time. And to put the time in context, here's kind of from left to right was the Vikings in the 70s all the way to Phoenix just a couple of years ago. You kind of see that they were gradually building these things faster and faster, and MER-2, which was actually Spirit, was the fastest one that they had ever built and was even faster, fell off again, faster than the Mars Global Surveyor Orbiter, which had the previous record. So it was slapped together very quickly, and as you all know, that it was a very complicated assembly. You have this lander, rover inside a lander, and then that was folded up and put inside an aeroshell and hooked to the crew stage, and then that whole thing went on top of the rocket. So it was certainly, they had no idea what they were getting into when they started to build it. So one of the things I got involved with on MER was rover egress development, and this is a picture of egress test number 45, I think it is, and this was tests 1 through 44. My boss at the time, Joel Krajewski, was leading all that activity, and he said, well, you know what you're doing now. Go ahead and fill out this test matrix and go through and do these different things and, find out where the limit was. And then Joel proceeded to leave the test bed and go down and have another meeting. So the first test we did after he left, found the limit. And I had taken this $100,000 rover, flipped it upside down and dumped its contents into the sand. And we kind of learned two things that day. One was that that was the limit. And the other thing was that you don't have to actually let the rover flip over to know that that's the limit. So in later tests, we decided it was fair game to catch it when it started to fall over. But the whole egress development plan was because the rover ended up being a lot larger than people expected. The airbags are a lot thicker, and we were honestly worried about the thing tipping over and landing on its face when we landed on Mars. And there's a lot of things that are out of control. So we did test after test after test. We inflated and deflated the airbags. If you ever wondered what the inside of an airbag looks like, here's one of the 4, and here I am in the airbag wrapped around the picture there in the fisheye photo. So I have red lung from spending so many hours in Times airbags. After I did all the egress work, I got invited to be on the team that physically built and put the rovers together. My title was an electrical systems engineer, and I thought when they asked me to be on the ATLO team, Assembly, Test, and Launch Operations, that I would get the cool job of suiting up in the bunny suit and spending all the time in the high bay. And when I found out that I would spend most of my time sitting in front of a computer looking at the spacecraft through a window, I was devastated. until like the first week I worked there, when I realized that everyone's suiting up in the high bay, can't snack on anything, they can't go into the bathroom when they want to, and they spent most of their time sitting, waiting on the people in the room, telling them what to do. So the high bay is a nice place to visit. It's not really a great place to work. So I was more than content working on the computers there, and all the skills that I had developed, setting up SEDS.org and all our late night hack sessions, putting together displays for the Flanders Planetarium kind of paid off, because all the people in the room, everyone else there was 10, 15, 20 years older than me, but no one had anywhere near the computer skills that I had. So I helped move things along a lot there. Again, for the pace of things, this was kind of the first mock-up where we put together with sheet metal to show what it looks like, and we went from that mock-up to Spirit, ready to fly, all integrated on the lander in just 2 years. When you send spacecraft off, you put them through a thermal vac chamber. In this chamber, we had pumped the temperature down to minus 150 degrees Celsius, and the vacuum down to 8 torr like it is on Mars. And this essentially shows all the robotic origami unfolding, solar arrays deploying, folding out. Pop up the camera next, I think. Maybe the high gate antenna. Oh, front wheels, body, the camera. And all these things, of course, we only did once when we landed, but had any of these, dozen-some deployments not worked, the missions would have, of course, been much less interesting than they have been for the last 5 years. And all this, we did inside a vacuum chamber, and, not the first time that we had done it, but, if anything doesn't work, you can't do anything about it. So that's about the rest of the interesting part of that. This is the last time and the first time that we ever drove Opportunity on Earth. So here it is. Spirit is in the back, up on blocks. Someone's ran off with the wheels. And we had lots of fun in the high bay doing things. We needed a calibration target to be able to demonstrate that we could drive somewhere and point the camera at anything in the scene. And that was the way that it navigated. So we came up with the rover secondary calibration target, otherwise known as SpongeBob SquarePants, which is seen in the corner of this photo. And it has like, a NASA certification sticker on it that someone had inspected it and that it was safe for the high bay. And this was actually our second choice, because what we really wanted to use was in the Orlando airport when you came in and out of Florida. There was a stuffed armadillo with a cowboy hat and 2 6-shooters. And we really wanted to use that, but bringing a dead armadillo into the high bay did not go over well. This is a picture of me and my friend Chris Voorhees, who designed the wheels. This is the last time that Opportunity was, set on its 6 wheels before we sent it off. So we get a little photo op there, and you certainly get a lot of friends as you do all this stuff. And when I give the short version of the talk, I point this out, and it's kind of take the time while you're working through your hectic work life to kind of enjoy the small successes and commemorate them appropriately. And this was certainly one of those times. You kind of, as you've seen, the rover's getting more and more complex. I like to show the contrast between this nice, beautifully rendered, everything looks perfect and it all looks like such a work of art, to what the thing actually looks like, which is a complete mess. And this is the part that you never get to see on Mars, because of course your eyes can't see your face. So this is a face only a mother could love. The robotic arm is all down here, the rat and the APXS and everything is all tucked in. And there was a team of women who did all the cabling for the rovers, and it was led by a woman who was old enough to be my grandmother, very, very sweet old woman, who is an absolute expert in this, and she had a team of Filipino ladies, and Filipino women are, I guess, the recognized experts in spacecraft cabling. But that's who we had that day. This was another one of those strange times in life when you realize kind of, what level you're working at and the environment that you're in. And this was the day before the Spirit launch, before they rolled back the tower. We all got the opportunity, for the folks that weren't working there on the daily basis, we got to go up and tour the rocket. Not only go up on the pad, but go up next to it, and everything was fueled and it was all sitting there. And you're expecting to go up there with people with M16s and security cameras monitoring your everything, and you can just kind of poke your head in and take a picture and walk out. But it was decidedly not that. It was, everybody suited up, they opened the door and they closed it behind you. And it was like, whatever you want to do, we trust you. And so we did all kinds of fun things, many of which we took pictures of. I had this nice picture. My brother would always take pictures when he was going on vacation. He would hold the camera out at arm's length, and you'd get the Grand Canyon or whatever behind him. So I have a picture, it's not in this presentation, but up at the top of the rocket with the rocket nozzle in the background. Got a good one of those. So it's just kind of strange though, but there are, certainly sacred halls in all aspects of different careers where you get to, and what you realize is that everyone around you is a professional. They know that you would be the last person that would ever cause any damage or take any risk because you've just invested the last 5 years of your life in it, and they don't need to watch you because you know what you're doing and you're not going to do anything stupid. So that was a fun day too. So there is a Spirit on the left, Opportunity on the right, morning and an evening launch. For both launches, I got the opportunity to do the NASA cliche. They pull everyone. I got to be one of the people who got to say "Go for launch," and the second time around was much easier. The first time we had Spirit launched, and the third time we tried. The first 2 days, there was bad weather, and you kind of knew that you weren't going to launch. And we got down to with like 2 hours, hour and a half, and we're all sitting in the Cape with the headsets on, watching everything, and it just never really felt real. On June 8th, June 10th, when Spirit actually did launch, that day I distinctly remember getting to about the T-minus 45 minute mark and breaking out into a cold sweat and shaking like you would not believe, and being physically ill just because you realize, oh my God, I hope it works, and that it doesn't blow up, and that I didn't do anything stupid in all our testing and everything, and I kind of calmed my nerves because we were going through all the polls and everything. And the worst part about it was we got down to like T-minus a minute and 45 seconds, and the test conductor, the launch controller for our spacecraft, was pulling around everyone in the room, and I was one of the people that he trusted the most, and we kind of went through the whole poll, and all this was all written out in a procedure very clearly, and what you do and what the responses were. And after we had done our last poll, he waited about 15-20 seconds. He kind of looks over direct at me and is like, "Chris, are we good for launch?" And I had no idea what to say because it wasn't in the procedure. And I'm like, "I guess so, let's go." So that was certainly, I hope everyone gets the opportunity to have an experience like that. So I won't tell you much about the trip to Mars, other than we had a lot more time to develop things. Here's a quick nasty chart. I gotta speed up and move through some of the stuff faster. This is the chart that essentially says which way is up. And when the lander deploys its pedals, how to decide what to do. And I did a lot of the work that essentially would demonstrate that all that stuff would work successfully. And went through and found things that weren't quite right from the Pathfinder algorithm that we inherited. And the Spirit, when we landed, it landed base pedal down, so you didn't have to do anything but just open up the pedals like a flower. And so we were all kind of relieved. Opportunity, we all took bets on which pedal it was going to land on, and I was like, oh, it's going to land on the +Y pedal, which is the one that was behind our head. And I placed that bet. There were 3 other guys on the team, so they all took one of the other pedals. And we got that first tone back from the surface that said, +Y pedal down. And my first reaction was, I won the bet. And my second reaction was, oh shit, I hope that algorithm works. So a bunch of engineers in the crowd, I have to show this chart in terms of landing on Mars, and the difference between landing on the moon. Landing on the moon, in some ways, is a lot more difficult than landing on Mars, because you have to do all of the delta V. You have to take all your rocket fuel, overcome the rocket equation. The convenient thing about landing in a place with an atmosphere is that you have an aeroshell, and the aeroshell takes away 99% of your kinetic energy. So that there's a lot of missions that actually have looked at dispensing with everything else between the aeroshell and the lander, because the parachute takes out 0.98%. These rockets on MER took out about 0.02%, and then the airbags take out the last remainder of a fraction of what you're doing. But the aeroshell really does most of the work. And on Phoenix, it was mostly the same, except the thrusters kind of took out this last fraction a little bit more than MER did. But it was all that effort into the propulsion system and the 60 kilograms of fuel, and the whole system took out 0.006% of your kinetic energy. So landing day, January 3rd, 2004, this was my office. I was 29 at the time. I'm 35 today. And, I was, at that point, 4 years from getting my master's degree from here, and I had no idea how I ended up in the room at the front of it that day. I found out that I had that job only about 4 months before landing. And it was one of those things where the people I was working with, they ultimately decided that he couldn't be flight director because he had too many other things to do. And I had so much experience with all that stuff from testing all those algorithms and working on the Atlas team that I was the guy for the job. And landing day, I was totally ready, and that was my job, and I was good at it, and I didn't have any fear at all that day. 4 months before, when we ran the first operational readiness test, and I was looking at the eyes of people who were 10, 20, 30 years my senior, with many more degrees and experience than I have, I was terrified that I would do something right. But everyone, they all had their job to do. I was fortunate to have my job to be the sexy title of flight director, but it is no more important than any other job in the room. So that was that day. Some notable things. Here's our lucky sheep in the corner, and our Mars clocks, everything kind of that day. So that was certainly a very exciting day, and very surreal. It was one of those things, you practice so much, and when it goes perfectly, it almost doesn't really seem like it's actually happening. So that was very strange. This actually was the first MER picture on Mars. Didn't really make many of the headlines, but the front hazard cameras snapped a picture, and at that point in the mission, the wheels happened to be there. So that was the first picture, although the better looking ones were these, Meridianum Planum, Gusev Crater on the top, Meridianum Planum on the bottom. And we'd only see those landers, of course, for a few more weeks before we left them in the dust. This is my favorite picture ever. Today I can give this talk without tearing up, but for a good many years I give this talk, I would tear up, just because of how much stress and pain and relief and everything that kind of represented, and what I wanted to do since I was your age and before that. That was kind of the day that it had all come to fruition. So it's still my favorite picture ever, even from Phoenix. I only suspect that whenever we have kids, that I'll have to say that that's my second favorite picture. So this is my third favorite picture, is the opportunity one. I have a different second favorite picture, which I'll show you in a bit. And the short version of this talk I give, one of the things you should know about NASA is that don't drink on the job unless the NASA administrator is filling your glass with champagne. So this was a quote that Time Magazine had in there from what I said when we landed: 2 for 2, 1 dozen wheels on soil. So that was a lot of fun. So I won't go into much about how the rover drives. I hope this animation works. Guess not. It's not that interesting. What you should know, though, is that the rover works through something called a goodness map. And there's a goodness index. And it's essentially looking at all the terrain around it and finding out what's least bad, and see if there's a path that it can work through. So there's very technical terms on stuff. One of the challenges with operating something on another planet, of course, is times. We had 6 different times to work with, Pacific time, Universal Coordinated Time, Zulu, Greenwich Mean Time. We had local solar time at the Spirit landing site, the local solar time at the Opportunity landing site, and then the spacecraft time internally was number of seconds since January 1st at noon, kind of cumulatively. Wonderful reference, but that's what it was. So these were the 5 different time zones that we had to work with. Those are actually all the same time. And then you had the complications of the amount of light time that it takes to get to Mars, when you have to send something on Earth so that it'll arrive at Mars at the right time, when you'll get something back when it's transmitted from Earth. So I wrote lots of programs from my SEDS experience to do all these calculations quick, so that One of the things we did was beeps. We'd turn on the transmitter for a little bit to let us know that we had passed some critical event. And I got it down to where I could, calculate to within a second exactly what would have come based on when we pressed the return key. And that impressed everyone a lot and was very useful. One thing that I found universally is engineers, enjoy the science. We like looking at pictures of Mars, but we like much better looking at pictures of the hardware that we sent there. So this is at Meridiani, the back shell, which we never could quite talk people into going over and driving up and looking at because we were worried about the parachute blowing around and permanently trapping the lander. Fortunately for Opportunity, though, the heat shield did land much farther away, and we got to go up and look at it. And so you can see springs on the surface. A lot of this stuff, when they sent this stuff out, this was all, I'm sure you've heard the ITAR words. A lot of this stuff was ITAR restricted, because this is all, ballistic entry, and you could use this for re-entry warheads for terrestrial stuff. So they didn't release all the pictures out. I just heard a story in the last couple of months about this picture that 2 of the mechanical engineers were absolutely terrified about. And on the other side of this Mylar, or underneath the Mylar, everyone likes to sign the hardware and do all that, and these guys had taken the Magnum 44 marker, the real one with a big fat head, and they wrote on the surface underneath the Mylar, because of course who will ever see that, they put their names in big letters, and that was, you could do it a little bit, the Magnum 44 was a little bit too much. And the thing about it is the Mylar on the other side torn off. And we did go around and take pictures of most of it, but they didn't. The names were a little bit farther under the sections that had torn off. So those guys were completely freaked out that they were going to be found out, a while later, but they never were. So we did some astronomy. There's moon transits. Here's Orion, the belt. And this is MERS version of You Are Here. This was a day in February. I hope everyone was decent that day because we took your picture. And Richard Garriott was talking about, just the whole experience of, and Carl Sagan's Pale Blue Dot. This is one of those humbling things. We're getting, every year we're kind of getting another version of this. The presentation I gave last night, actually, Earth, on the bottom of my presentation, was the European Rosetta mission. Did a flyby Friday morning, took a picture of the Earth. I put it in the bottom of my slide Friday midday. But we're certainly, more and more of the planet is getting the perspective of our place in the universe. I like to close out my MERC presentation with this one. This is kind of when still the whole exploring thing was pretty new, and everyone in the control room when we put the plans together every day, it was kind of getting to the point where we were taking all this for granted. And I kind of had to remind everyone this. This was the first crater we were going to go look inside on Spirit, and we were going to go up and look over the edge. And so this is what it looks like when you plan it. You get this picture of the rover, and of course you can't see in the rendering what it's going to look like because you haven't been there yet. And the next day, the data comes down and you fill it in, and it's really like being there. Steve Squires has given lots of talks about Steve Squires and Ray Arvidsson about how well these rovers have allowed us to kind of walk across the surface of Mars. Of course, Steve also says that he could do the same amount of science in an afternoon if he were suited up in there. But robots are doing a good thing for now. Went on to some other design projects, built a garage for a while. Now I'll try to blaze through Phoenix as quickly as I possibly can. As you probably know now, looking at the history of NASA stuff never stays the same. This is a chart where they're planning all the different missions, and this one happened, and that one happened, and that got canceled, and that one's no longer there, and then the mission that's here got delayed. And so the best laid plans go by the wayside, of course. So picking up the thread from Mur to Phoenix, Phoenix's charge was to finish the O1 lander and don't try to change anything, just make it work. So we had a lot of cases where something was designed, perhaps wasn't the best way to do it, but it would work. Even though we could make it better, we chose not to. And Phoenix actually, inversely, inherited a bunch of stuff then from MER. The UHF relay, we actually put a redundant antenna on there. The batteries we had proved out. And now MER gave some instruments back to Phoenix in terms of the technology for using them. I'll skip the details of the mission and where it's at. There was our landing site. A little note about the landing site. The ellipse that we ended up flying on was this one. And a couple days before landing, we have the opportunity to tweak where we are in our landing ellipse, and this is kind of the 3 sigma uncertainty, depending on how the winds go and how you torque when you're re-entering, where you'll end up. And we were, I think, right here in the ellipse. And we decided, everyone wanted to be right here because there was a big rock or a big hill in the middle of it. But we decided, well, we're in the ellipse. We shouldn't change it, leave well enough alone. And it's a good thing we did. If everyone remembers the picture from Phoenix re-entry, we got, the lander was here in the sky with Heimdall crater in the background. It looks like we were parachuting right into the crater. But had we done the trajectory correction maneuver, odds were fair that we would have landed in the crater in terms of the magnitude of the change we would have made. So it's good that we left it well enough alone. Keep dropping that thing. So Phoenix had its own version of staff up and robotic orbit origami, a little bit less complicated. I'll skip the instruments. Just a little thing from, you talk about PowerPoint spacecraft versus real spacecraft. So here's the PowerPoint version, and then this is the actual thing in the thermal vac chamber. So it's kind of nice to see things evolve when you're working on these missions. We take the spacecraft and put it through a lot of different tests. When we had a mascot, the alien. Apparently the alien goes all the way back to, I think, Pathfinder, and it had a tin hat in honor of the EMC tests so that it wouldn't get its brain cooked. Thermal vacuum testing, and then another one of those moments where you get to stop and take pictures. What was kind of nice about this one is on Phoenix we were working with the University of Arizona, Jet Propulsion Laboratory, and Lockheed Martin, and we had the opportunity. We were such a closely knit team that it didn't really matter what your badge was because we spent so much time with each other. So we have, people from all 3 different organizations who are frequently all together and working on things, and it was a very close knit group. So this is another fun picture, one of those visits to the high bay. For Phoenix, I led the design of the landing day events in terms of after we landed, everything that happened to deploying the solar arrays and reconfiguring everything and deploying the instruments and taking those first few images. And I worked intimately with these ultraflex solar arrays that you see now in all the Orion designs built by ATK. And I designed the algorithm with a team that covers the deployment of the solar arrays, and that's the one super critical thing after we touch down. You have to get your arrays out, because if you don't, the mission is over, because there's no plug. So this was the first time that we had ever deployed the solar arrays on the spacecraft, and we would only do this actually one more time before we went to Mars. But that was another fun day to be in the high bay. So shake it and bake it and spin it, test out all the deployments and separations. This is what the solar arrays look like before they're quite completely deployed. Kind of like you would expect. And another opportunity, kind of a career standpoint, something that you should make sure that you are always involved with at every stage of your life is being in a mentoring or an apprenticeship or a mentor relationship. I realized on Phoenix that I had the great advantage of always having wonderful mentors and being in a wonderful mentoring environment, from Dr. Boynton to Susan Brew to Sridhar and all the other people at the university and everywhere else that I worked. And I kind of took it for granted, actually, up until the point when I had a terrible mentor. And it was at that point that I realized how fortunate I had been up to that point. And this was an opportunity. I was in the high bay with a retired engineer. His name is Frank Locatell. And Frank is one of the most senior and experienced mechanical engineers of spacecraft in the world. And we hired him on Phoenix because we wanted to come and look at the spacecraft and tell us if we were building it right. And the workmanship details and how the Filipino ladies tie up the cables, if they tie them up correctly, and if the cable, the piping is, he just can kind of look at the stuff and tell you if it will be a problem. And I had the opportunity in my capacity as a system engineer in Phoenix to kind of lead him through and provide him all the information and context for what he was looking at so he could tell me. And the other interesting thing about Frank, at the beginning of the talk I told you how about Voyager 2 started my career kind of in robotic space exploration. Frank was the chief engineer for mechanical engineering on Voyager 2. So I got to, kind of work with one of my personal heroes in doing this stuff, and it's also something I hope everyone else gets an opportunity to do. Seek out mentors. If you're in a position where you have the opportunity to mentor someone else, and it doesn't matter, well, I'm only a sophomore. It's like, well, it doesn't matter. There's a senior in high school who looks up to you. So you can mentor those folks, and that goes that way for your whole life. Got to take a fun ride with the Phoenix spacecraft to Florida on the C-17 aircraft that they ship it in. Did lots of processing in Florida, and then one more time had the opportunity for the Phoenix launch to say, go for launch. This chart I just dropped in here real quick, kind of comparing the two things. I like the MER drives, Phoenix digs. Peter Smith always joked about our vertical mobility and how MER didn't have any vertical mobility. Another thing I'd like to point out is Phoenix had 16 megabytes of flash memory, and MER had, by comparison to that, a massive amount. But of course, everyone's cell phones have much more than that amount of flash memory. But you make do with what you have on these spacecraft. And the last one, of course, is that MER is still alive, Phoenix is dead. So here's my second favorite picture. This is, my sigh of relief seeing the solar race deployed, of course the surface of Mars and the northern polar region, and then a robotic arm with a scoop of soil in it, kind of on its way to the first TIGA analysis. So this was kind of the capstone picture for Phoenix. I'll skip through the operations. So we're getting close to the end of the Phoenix mission. When we first landed, we were in land with the midnight sun. The sun never set. We were above the Martian Arctic Circle. And that meant that we could, do a lot of operations because the sun was kind of always there, giving you a little bit of power, not a lot. It also never got very high in the sky. At high noon, the highest the sun ever got was 53 degrees. And at midnight, the sun would be like 8 degrees. But as we got farther and farther in the mission, that starts to go farther and farther down and things start to break, and I'll show you some plots in a moment what that does to us. So hope everyone has had a chance to look at all the images in detail. One of the more famous ones in terms of the confirmation of the discovery of water ice was between Sol 20 and 24 of one of the trenches. You could see that there was some white material here this day, and then 4 days later, a Martian had absconded with it and ran somewhere. And the only other explanation was that it was water ice that had sublimated. So that's the one that they used. One of the robotic arm scientists, gave a test for everyone who was working in operations last summer. I don't know if Carrie is still here. It's not. Carrie, I think, passed this test. I failed. It was, name all the targets that we had been to, and we had the, of course, the fairy tale theme of naming things. So there was a lot of different things going on. Phoenix was unique in that, we went from the atomic force microscope, where we could see things down to a micron level scale, where we can examine crystalline structure of the materials that were on the arm. A feature of the robotic arm scoop that I did not even know about till the first time that we used on Mars. There's a little indentation on the front tip of the scoop, and if my eyes are the robotic arm camera and this is the scoop could turn kind of upside down and point it right at the camera head, and you could take a very close focus and look at this thing that is about 1.5 millimeters high and see all the kind of this grain structure of how the soil bonds to itself. And then of course the surface stereo imager for these broad pictures, and then with the LiDAR we could fire up into the atmosphere 5 kilometers. And this was one of the favorites of a lot of folks, as kind of the green cast of the famous Hubble telescope Eagle Nebula. The optical microscope and the atomic force microscope certainly gave us an interesting scale of things to look at. Did lots of atmospheric science with dust devils and windsocks, and this was clouds and precipitation we saw on Mars. The clouds was kind of an interesting thing, and the snow on Mars, didn't really realize actually until almost the mission was over, the explanation with this. You would see frost, and the LiDAR would see these little speckles, and we would see on the mirror that was looking in the windsock, we would see little speckles. And someone actually finally came up to the correlator that on Earth there's snow in the Arctic regions that's called diamond dust. It doesn't look like the white flaky stuff that you see when you go skiing. It's actually micron level ice crystals, and because of the physics and the pressure and the dew points and things like that in the Martian environment, that's the type of snow that you get on Mars. But we found that it was routinely snowing on us. This was the chemical and thermal detection of the water. Bill Boynton, my advisor and employer when I was undergrad, wanted to call this sample the Wicked Witch, so he could say that she was melting. And if you didn't see the press release, Bill does this wonderful thing where he puts on a witch's hat during a NASA video press release and does an impression of the Wicked Witch of the West melting. It was grand. The wet chemistry cell detected, let's see if I get this right, sodium chloride, not sodium chloride, magnesium chloride. Am I getting that right by looking at these chemicals? And calcium carbonate, chalk, and of course also the acidity of the soil, which was a surprise to some, and for other folks it was obvious, but these are the way of the science. Everyone has their theories until the data proves otherwise. And then people interpret the data in different ways. So getting to the end of the Phoenix mission, for the last 60 sols or so, this chart governed my life. The green plots describe the amount of energy that we get in. And as you can see, it's sloping down kind of as the seasons go on. And eventually the sun sets, like Sol 212. And Sol 212 was February of this year. And for reference, Sol 120 was back around September of last year. The thick blue line shows the absolute minimum amount of energy that we need to survive. If we turned everything off and we kept things just barely warm enough so that we could exist, couldn't really do any science, but we could exist if we kept the green line above the blue line, and then the red line kind of showed if we're going to do anything useful, where we had to be. And of course, where the two lines intersect, you have to make difficult choices. And as mission manager, one of the difficult choices I got to be involved in making was exactly when do we chew off our arm to save our own life? And quite literally, it meant turning off the robotic arm to never be used again in the mission, and turning off the TIGA instrument to never be used again. Once we turn them off, we turn off the heaters, and the electronics might survive. They probably wouldn't. Even if they did, we wouldn't have enough energy to power them. So that was kind of a permanent decision. And another interesting point in life, Bill Boynton, the PI of the TIGA instrument, of course, wants to get every last ounce of life out of his instrument. And here I am in a position to make that decision, which will, of course, affect his career in terms of the science he's going to get out of his instrument. So we evaluating this on a daily basis, and the weather was changing, and the numbers are moving all around. And one thing that we didn't take into account until it was too late to really change the plan much was the clouds. As we got later and later into the fall on Mars, morning clouds would appear. And clouds would come in at 6, 7, 8 in the morning as soon as the sun rose, and they would stay around until noon, until they burned off. So that meant that the amount of power that we were getting in was a lot less than we expected, and of course you can't do anything about it. So we ended up ultimately doing our last TIGA run and turning everything off on Sol 157, and that same day we were hit with a slight dust storm. But in terms of the situation where we were at, it was not survivable with where we were at. So the spacecraft kind of went belly up for a day. Came back the next day via all its kind of programmed responses, and we spent about the next week kind of fighting to keep it alive, and we ultimately lost the fight about a week after that, where we were kind of planning the end game mission and doing all that type of stuff, and I think it was around Sol 161 or 162 was the last that we ever heard from him. And then we spent the rest of November kind of searching just in case it happened to pop back. But it never did, and we stopped listening for good around I think November 28th of last year, and haven't listened since. Everyone always asks me a lot, will it come back after winter? I would advise you to bet against it. I should have put in a picture of High Rise, just released last week, showed, go find it on the net, that showed the lander kind of barely discernible because they're taking it with a very small amount of light and surface haze and all this type of stuff. But you can clearly make out the lander. What you can't clearly make out is solar arrays. And the reason why I advise everyone to bet against it ever coming back is these solar arrays are these very dainty things. And even though the material holding up the solar cells is this Vectran kind of Kevlar type material that could take a bullet, the stuff that's holding up that Vectran is these carbon epoxy graphite spars that, you know, if you put your arm on it, you would crack it right over it. And if you put a meter of CO2 ice on it, I don't think it's going to survive either. So I guess we'll see in another month or two, you know, and the pictures get a little bit clearer if there are any solar arrays left. But we went through a period of the sun set permanently, where we're kind of in the Arctic winter, and the lander is encased in CO2 ice, still is right now, and is going to start to come out of it, and the sun will get high enough that they'll try to listen for the lander, probably starting January or February, but I wouldn't expect much. If the lander hasn't physically broken, there's all those types of things where, you know, if you take any piece of electronics and put it in the freezer, it probably doesn't work that well when it comes back out. Spacecraft hardware, of course, is designed a little bit better than that, but all it takes is one solder joint to fail, or one integrated circuit chip to fail, and, you know, 1 in 10,000 different parts do that, and the probability of the whole thing surviving through that is low. So the sun has set on the Phoenix mission, and it certainly was a great experience for the University of Arizona. It was wonderful as an alum and as a SEDS member to work with all the people that I had worked with when I was here in doing that mission. It was a success. It lasted longer than anyone expected, and it kind of all played out, I guess, as good as anyone had hoped. And it was a very strange experience at the end of the mission. It was everyone, of course, is still flabbergasted that Spirit and Opportunity are still going. Tomorrow, tune in to see if Free Spirit, Episode 1, is showing any promise of success. The commands have already been set up to the rover, and tomorrow they're going to find out if the first steps they're going to try to get out of that area on home plate are going to work out. But Phoenix, you know, kind of knew when we were going to die, we knew how we were going to die, and we just had to pack everything in getting up to that point. And it all kind of played out as everyone expected. So, and the other thing is these days, people ask me, well, what are you up to now? So I made a choice last fall after being presented with an opportunity essentially go off and do something that I always wanted to do. And you know, in one hand I had the choice of I could stay at JPL, I could go work in the Mars Science Laboratory and kind of land on Mars for the 4th time. If you've done it 3 times already, it is fun. I recommend everyone do it at least once. But I'm in the surprising situation in life of saying, once you've landed on Mars 3 times is pretty good. Other opportunities working in Earth orbiters. I'm a planetary guy, so Earth orbiters didn't excite me all that much. So I ventured off on my own, and I made the decision to quit JPL yet again. I'm a repeat offender. And my reason for doing so is because I was like, well, the worst thing that could possibly happen is that I would end up back at JPL. And that wouldn't be so bad. So I'm off doing space things, doing something that I love. I recently came to the realization in the last few weeks that, you know, the other unfortunate thing is I can't tell you what I'm doing because I'm bound by non-disclosure agreement to talk any of the details. I can't even tell you the name of the company, so that's why I'm from LewickiDyne Systems, which is always my placeholder name for my empire that I would be building. But I came to the realization recently that, you know, if I were to be diagnosed with a terminal disease today, you know, and had 6 months to live, what would I want to do? Well, I'm doing what I'd want to do. So it also is an awesome place to be. And it so happens that I'm looking for an intern for the spring. So if anyone is interested in, you know, spending some time in California and working in the most loosely organized of startups in the most unprofessional work environment that you could imagine, and something that you can't tell your friends about, and you have to sign an NDA to even do the interview. Look me up and we'll talk. So that's the end of my presentation. I'll take any questions now if anyone has any. Yes, Josh.
To help all potential applicants here, can you at least give them a major you're looking for?
Doesn't matter.
We have library science majors here.
Yeah, I have a slight preference to engineers, but it's a very interdisciplinary activity. Business majors, legal would be pretty good. Maybe I would turn down art majors.
When do you want them, like January? You're saying? For spring or after spring?
No, spring and after spring.
Like May.
That would work too.
I'll post it to you. So.
Yeah.
How long do you need someone for?
It's negotiable.
I've got some time early in the summer before we go to study abroad.
We'll talk.
Okay.
Just maybe you could talk a little bit about Yuri's night and some of
Sure.
that involvement, and let these guys know how they can get involved too.
Yeah, Yuri's Night, I got involved with the very first year, 2001. I had not yet met Loretto Hidalgo-Whitesides. I hope everyone here has met her. I can't imagine how you would avoid meeting her. She knows everyone, and she's a connector. Her husband, George Whitesides, was a colleague at Blastoff. And George told me, hey, we're doing this thing, we're going to have this party, and I'd like you to help get organized it. So the first few years, I put all my SEDS internet experience into helping him, do webcasting and websites and streaming and all that type of stuff. And I've kind of been very loosely involved ever since. This year, since I am not slave to an aggressive flight project launch schedule, I'm volunteering a little bit more time. So I'm working with Ryan and Grant and other folks trying to make this year's Yuri's Night as best we can. We're always looking for volunteers, no experience necessary. You get everything that you need. And Yuri's Night is it's all aligned with everyone's SEDS experience, where they really just want to kind of celebrate space. And you need something to be the focus of that, so why not Yuri Gagarin? And Yuri Gagarin launched on April 12, 1961. Shuttle Columbia, Columbia, STS-1, launched on April 12th, 1981. There were a few other April 12ths in there. Loretta's birthday, kind of suspiciously coincidentally, is April 12th.
ISU.
Yeah, ISU is April 12th.
Yeah.
And there's another one that I saw recently was in April 12th. But
It'll be our 10th anniversary too. So.
yeah, and one thing we were joking about. Actually, Elon Musk was joking about this to Ryan about well, why not Korolov's day? Because Korolov was the lead engineer of the module that Yuri was in. So why not? Why not? I was thinking actually we should talk about the next telecon. Why not Valenti, or the first woman in space, who is still alive? Yeah, I think she's still alive, but I heard that she's very reclusive, so that would be a challenge for us. But if you don't have the gumption to host a party, certainly look one up or motivate someone else into hosting one for you. We're getting started uncharacteristically early this year. Usually it's a mad scramble in the last 3 weeks before the parties. The flagship event is, I believe, going to be in Ames again this year. And all the flagship really means is that'll be the biggest, hugest one that all the celebrity rock stars will get invited to. But there have been many other prominent events. I've been to the Colorado one at least once, if not twice. I remember spending the evening talking to Bob Zubin, I think, for the first one. So it's a nice mixer. No other questions? No lingering things you want to know about the Rovers or Phoenix making the jump to student to professional careers? All right, we'll call that done. Thanks.